Hello everyone and welcome again to this class. And in this class we are going to discuss the new topic. And if you remember, in the previous class we had done with some problem based on this canonical transformation, and we have calculated some method through which we can figure out that whether the given transformation is canonical or not. So I have provided you 6-7 problems, and out of that 2-3 I have calculated and tried to solve it in front of you, and then the other problems have been already solved in this PPT, so you can go through that. But again, I'm requesting you to please calculate yourself and try to match with this solution which I have given to you. So moving on to the next topic is the infinitesimal canonical transformation. So we have done through this canonical transformation that demands that when you transform your old coordinate qp to basically the canonical variables qp small to the new canonical variable, that is capital Q and capital P, that we have gone through, and that canonical transformation demands that the transformation must preserve the Hamilton canonical equation, that is that q dot equal to delta h upon delta p, and p dot is minus delta h upon delta q. So this is for canonical equation must preserve. If we go from small q dot to capital Q dot and capital P dot, and then the modified Hamilton principle, the form of that must be preserved. So the infinitesimal word which is attached to the canonical transformation is just that when you're transforming transformation is very, very small, that is infinitesimal change in the canonical variable, that is qi pi, and that infinitesimal variable is denoted as when you transform from q to qi and small q to capital Qi, this is delta Qi is going to be infinitesimally small, and that transformation must preserve, as we did in the canonical transformation, must preserve the canonical structure of the Hamilton's equation. Okay, so that Hamilton equation has to be preserved. That this canonical transformation is one that in which when you transform your small q, small p to new variable capital Q and capital P, then such transformation, the Hamilton equation remains unchanged, and then the transformation is represented as this q is given in equation 1, that is this small change in q and this small change in infinitesimal small change in p variable. Okay, so this delta q and delta p are simply infinitesimal change in the coordinates and the momenta, and they goes to, with this small infinitesimal change, this qi goes to this capital Qi. This is the transformation, but keeping that the canonical equation of motion and the Hamiltonian has to be during the transformation remains unchanged. Okay, so then when you talk about the transformation, then you talk about the generating function, because in canonical transformation we have, you remember, we have 4 type of generating function: f1, f2, f3, and f4. So whenever we talk about some transformation, and that is the canonical transformation, then we need a generating function. So there must be some generating function related to some infinitesimal canonical transformation. But if you see equation 1 here, then if you put in equation 1 delta Qi and delta Pi, if you see delta Qi and delta Pi here is 0. So then this is simply this Qi goes to Qi and Pi goes to Pi, and this is nothing but the identity transformation, that old coordinates small qi goes to capital Qi, and that, if you remember, this identity transformation is given by the generating function of type 2, that is f2. Okay, so in this case let's suppose that the generating function is type 2 f2, which generates the identity transformation with some particulars, as because the f2 generating function is given as this qp. Okay, if you remember, F2 depends upon this Q and capital P and this T, and that is if this is QP, then this transform as the identity transformation, and the corresponding derivatives with and you know that every generator F1, F2, F3 has their corresponding derivatives. So that's going to give you that what kind of transformation that particular generating function is going to give you. So that the corresponding derivative for this F2 is this Pi and Qi. From here you decide that whether that is going to be the identity transformation. So if you see that this is Q and P, so if you find out this Pi, that is delta F upon delta Qi, so this is equal to capital P from here, and then if you find Qi from F2 upon Pi from here, if you see that this is going to be Qi. So this is going to be the identity transformation. So one thing is clear that that my generating function for infinitesimal canonical transformation is going to be have some part of this Qi and in this F2, and then in this F2 generator, if I add some infinitesimal component with some function which is going to be my generator. Okay, this G. So this is how we are transforming, trying to create our generating function for the infinitesimal canonical transformation, where naturally this epsilon is some infinitesimal parameter of the transformation, and GPT is arbitrary function, a phase space, because in momentum space we have and time. So from this equation, if you see the transformation equations are found to be, because you see that when I'm saying that F2 is going to be the generating function is a sort of F2, and then my generating function, which is GP, is my GP, which is related with my F2. Then this has to preserve this these corresponding derivative Pi and Qi, which is related to type 2 generating function. So if I say Pi, this Pi, from here you have Pi from equation 2. So if we say delta F2 upon delta Qi, so I'm going to differentiate this expression with respect to Qi, a small Qi. So the small Qi is here, so it's going to give me Pi. You have Pi, and then epsilon is there, and delta G upon delta Qi. And then the second differential is this Qi, and that is F2 upon capital Pi, F2 upon capital Pi. So I'm going to differentiate this F2 with respect to this capital Pi. So this is going to Qi, and then epsilon and delta G upon delta Pi. One modification we can done here, that this P, because I have this Pi is going to some Pi plus some delta Pi, and this is basically some epsilon. So I can replace this being the transformation is being so infinitesimal. So for differential purpose, we can replace this Pi to a small Pi. So I can write this as this delta G upon delta small Pi. Okay, so I'm going to write this as this delta G upon delta Pi. Now, if we compare equation 3 and 4 with equation 3 and 4, this equation and 3 and 4 with equation 1, that equation 1, if you remember, the equation 1 is capital Qi going to Qi delta Qi. So my equation 1 is this Qi is Qi plus delta Qi, and this capital Pi is Pi plus delta Pi. So if you're going to compare this with these 3 and 4, so what I'm going to get is this if Qi first equation, so this delta Qi here is nothing but the epsilon delta G upon delta Pi. Now this is this I can replace by small Pi, so this is going to delta Qi epsilon delta G upon delta Pi. This is delta Qi, delta G upon delta Pi. And then if I compare this is Pi. This is, say this is Pi, because capital Pi is here. So now capital Pi is here. So if I write this is going to be Pi equal to pi minus delta pi. Okay, so this minus delta pi is my epsilon delta g upon delta qi. Okay, so minus delta pi is epsilon delta gi upon delta qi. Okay, so therefore this is going to be my transformation equation, as I have transformation equation related to, if you remember, transformation equation related to my generating function f2. The generating function f2, I have differential of pi and delta f2 upon delta qi, delta f2 upon delta pi, and so we have our generating function is here epsilon, this g, basically not epsilon, this g. So this is going to have the corresponding differential equation, and the displacement is like this is delta pi and delta qi. So I have delta pi and delta qi related with my generating function for the infinitesimal canonical transformation is epsilon g upon pi and epsilon g upon qi. So when you are transforming the canonical variables to various infinitesimally small amount, that is going to be the epsilon, so that the transformation is transformation preserves the canonical equations of motion. So and then we need a generating function for that, and that is going to be the g in our case, and that luckily is got to be my f2 generating function, which depends upon, that is related with the f2, that transform identity transformation, because when I go to q to q plus some epsilon, that is delta q, so that is going to be some epsilon, very small transformation, delta q, this is my delta q. So that is effectively, when it is tending to 0, that my transformation is going to be the identity transformation. Okay, so therefore we can consider this my g is as a generating function of the infinitesimal canonical transformation, and the corresponding differential or derivatives are going to be in equation as given in equation 5. These are my generating functions. These are my corresponding differential equations. So every generating function has the corresponding differential derivatives. So this g, which is the generating function of infinitesimal canonical transformation, is my generating function. Okay, fine. So now if I take the Poisson bracket of this q with respect to this transformation g, because you see that in terms of the Poisson bracket, you see that when I take the q with q with h, so what I get is q dot, that is the canonical, that is going to be delta h upon delta p. If you remember, this is the Poisson bracket. This is canonical equation of motion in terms of Poisson bracket, and then you have p with h. This is going to be p dot, and this is going to be minus delta h upon delta q. Okay, so this we have already gone through that h is the generating function of this system, that is depending upon q and p, and so that is going to be the canonical equation of motion. So the same analogy, if I try to take the Poisson bracket of q with respect to g, because g here is my generating function in this case, so I can write is with the base is qp, because it depends upon a small q, a small p. So I can write q with respect to g. The first function is q and second function is g here. So according to the definition of Poisson bracket, that is qp and pq. So now here this term is going to be 0, because the q with respect to p is delta q by delta p is 0. So there's no change in q with respect to the momenta. So I have the second term is 0. So I am left with the first term, and here we have qi upon qj. This is nothing but my delta ij and then delta g. So when I equal to j, So when I equal to j, I'm going to have this sum is going to survive, otherwise this all going to be 0. So when this I equal to j, I have, when I place I equal to j, so either I can write I can write j, that doesn't matter because I equal to j here is in this case. So what I have is this q, Poisson bracket of the q with respect to the generator of the ICT, that is G is going to give me delta G upon delta Pi. So that is if you compare with this, that is Q with H is delta H upon delta Pi. So Q and G is delta G upon delta Pi. In the same way, you can find out P with respect to G. So you can find similarly. So I have delta G upon Q and G is delta G upon delta Pi. So I can write delta G upon delta Pi. If I multiply it by the epsilon, which is the infinitesimal transformation from old coordinates to the new coordinate, and this is parameter. So this is going to be epsilon delta G upon delta Pi. And you see that what is this epsilon delta G upon delta Pi? This epsilon delta G upon delta Pi is, this is my delta Qi. Okay, so this is my delta Qi. In the same way, you can figure out your this Pigi, that is going to be minus this is epsilon, because if you calculate this this Pig and then this is a Poisson bracket of this, so you have summing over I, that is delta Pi upon delta Qi, and then you have delta G upon delta Pi, and then minus delta Pi upon delta Qi, and then delta G upon delta, this is going to be delta Pi, and then the delta Qi. Okay, so delta P upon delta Qi, this is going to be 0, and so this first term is 0, so you have nothing but delta upon I. So you have with a negative sign delta Pi upon delta P, this is going to be Pi. So Pi, you can have sum over j here, sum over j here, sum over j here. Okay, I is already there, so I'm summing over j. So this is Pj, and then you have delta G upon delta Qj. So this first is going to be minus delta Ij, and then you have delta G upon delta Qi. Okay, so y equal to j, this is nothing but delta G upon delta Qi. So you have delta G upon delta Qi. If I multiply by this factor epsilon, then this is going to be Pi, as we have already calculated here. Delta Pi is minus epsilon delta G upon delta Qi. Okay, so you see that this is G being the generating function of the infinitesimal canonical transformation, that if we take the Poisson bracket of Q and P, this is exactly giving you the analogy of this Hamilton's canonical equation. If you put G as H as the Hamiltonian of the system. So if you for example, if you put this G is my Hamiltonian is of the system, and then epsilon is my time dt. Okay, so change in time. So what I'm considering here is the transformation in terms of the time. So my transformation is dt, epsilon is dt, infinitesimal time change in time is because the canonical variable is q, p, and t. So I am considering here this epsilon is the infinitesimal change in time dt, and the generating function is the Hamiltonian. So then from the relation that delta Qi, my delta Qi is this Qi Poisson bracket, and now my H is G, and this with Qi, and epsilon is my dt. Okay, so we know that Q Poisson bracket of Q with H is my Q dot with respect to t. So what I'm going to get is dt is here, and the Q dot is basically dq upon dt. So this is going to be dqi dot, and then similarly for dpi from here, this is going to be, if I put Hamiltonian is here, this is going to be pi dot, so that is going to be delta pi dot. So I have two relations, that delta q is delta q dq dot, and this is delta p is dpi dot. So what I'm going to get is this is the time variation of the time translation, the translation in time compared to time is is going to be my change in the variable. So the conclusion is that when your generating function is the Hamiltonian, okay, so when your Hamiltonian of the system is the generating function, so what we are going to find is that the infinitesimal canonical transformation, what you are doing changes the canonical variable, that is q and p, that is delta q and delta p, that is delta q and delta p, by an amount equal to change in their values in time. That is if you have seen that it is delta q dot and it is delta p dot. Okay, so that is giving you, if your generator is the Hamiltonian. Okay, so then what you are seeing, the system, the transformation of the system in a time interval dt. Okay, and that can be described by the infinitesimal canonical transformation that is generated by the Hamiltonian. So if you're seeing the motion of the system in time interval dt, so you are in the same phase space, and if you're seeing the transformation of your system from one point in configuration space to the another point in time interval, the very small time interval, infinitesimal time interval delta t, so that can be described by the infinitesimal canonical transformation of that is generated by the Hamiltonian of the system itself. So if you sum over all these infinitesimal canonical transformation, that is from certain time t0 to t, that is equivalent to the single finite canonical transformation. Okay, so this is what the concept is, that if your canonical transformation is represented as the motion of the system in time, then this is going to be Hamiltonian is going to be the generating function of the infinite canonical transformation. So what I mean to say that when your generating function is the Hamiltonian of the system, then this what you have, infinitesimal canonical transformation is basically system transformation in time. So we will see further that if my g is h, then that is what I'm saying is the system is being transformed in time for this small delta t, and then if I sum over all this is going to give me the total transformation of the system or canonical transformation in time t equal to t0. So this is basically one thing, that when you're dealing with the Hamiltonian, that the infinitesimal canonical transformation is going to give you the transformation of your system in the time. Okay, and the second thing is so this last line, you can see that the Hamiltonian therefore is the generator of the motion of the system in its phase space or with time. Okay, now the second thing we are going to see is that the generator could be this transformation in time of the two kind maybe. So how does a function changes under canonical transformation? Okay, so a canonical transformation, changes the phase space variable, a small qp, to new variable capital QP, such that you demand that the Hamilton equation is being preserved. Okay, that is q dot and p dot is as given by the old Hamiltonian is going to have the capital Q dot and capital P dot and given by the new Hamiltonian. Okay, that is, but this transformation can be viewed in two ways, that is known as, one is the active viewpoint, and the second is known as the passive viewpoint. So we're going to, we are going to talk about the active viewpoint, but what is the passive viewpoint of that? In the passive viewpoint, what you have, the system is fixed. What you are going to do is you're just transforming the coordinate system in which you are working. Okay, so the system is fixed, but you change the coordinate you describe, like when you do in xy coordinate system, Cartesian coordinate system, then you move to the polar coordinate system, but the system itself is not moving. Okay, so the system, if we have one point which is defining the configuration of the system, that point is not moving in space. That you itself is like you just changing the representation of that particular point in space, phase space, in terms of the another coordinate system. So that the point in phase space, the physical state of the system remains the same. It's not going to change, and that you merely changing the new set of canonical coordinate, that is q pi, in the different phase space described by the different canonical variables. So as x y is defined in terms of an r theta, that is what the passive view of that you are just changing the coordinate of the system and not the system's state of the system. Okay, so this is analogous to changing from Cartesian to polar, as I told you, that the point doesn't move. But in active view of the transformation of the system is that the system itself is changing in phase space, going from one point A, and which has this variable QP, and to some point P which has some variable P. So in this canonical transformation, the system configuration of the system is being changed in the same phase space. So we imagine that the system is moving from point A, where it is defined by some canonical variable, a small QP in phase space, to some new move to a new point in the phase space where the configuration of the system is being defined by some canonical variable. This is some capital Q and capital P, and that transformation is, if this is canonical transformation, and that if it is infinitesimal canonical transformation with some generating function g, and then if you sum over all this, then you're going to get your whole canonical transformation. So in this, the function does not change in functional form, but rather it changes its value, because it's changing the system. The whole changing is going from one point to another point. Okay, so because earlier in passive view, what happens, your function is in terms of xy, it changes to function in terms of r and theta. Okay, but value does not change because the system configuration is not going to change. But in active, what is happening, you have qp, and this function is changing in terms of qp. So the form of the function changes. Okay, the form of the function changes because the system is actually changing its configuration in the same phase space from 1 to, yeah, here is only the coordinate has been changed. Okay, so this is the viewpoint of that active transformation or the passive transformation. So we are naturally going to view the active point of view of that. Okay, so if we consider that this infinitesimal canonical transformation of a function, that is some depends upon qp to some qp, that is we normally viewing in the active transformation, then where my q, this q and p, the new coordinates is canonical variables, is related with this delta qi, delta pi, which are infinitesimals, and that is going to be considered to be infinitesimal canonical transformation. So this change in value of this function, when this function f is going to change, so the value of the change, because we are considering the active view, so the value of the function is going to change, not the root form of the function. Okay, so the change in is going to be delta f, because my function value now depends upon q and p in the same phase space, and then from earlier which depends upon a small q and a small p. So that is given by this, because q is q dot qi, p dot pi, and this is going to be qpi. So we can write it as this transformation as this transformation, because when you differentiate that, when you write when you write delta f upon delta q, say like this is some qj. So what you write is limit delta qj tending to 0, and then the function value of the function on qj plus delta qj, and minus value of the function on qj divided by delta qj. Okay, so this is what you have. I have qj plus delta qj minus this function's value on the qi, and so this is going to be my this multiplied by this delta qi. So this is why this has been written like this. Okay, in the same way for this pi function depending upon the momenta and the change in momenta, so this is going to be this term. Okay. And now we know the relation from a canonical transformation, because G is the generating function of the canonical transformation and depends upon Q, P, and T, and then corresponding derivative is delta Qi and delta Pi. So we can write in place of this delta Qi and delta Pi here in this thing. So what I'm going to get is this change in the function value of the function is like if I take this epsilon is some constant I can take outside. So this is the first function with respect to Q, second function. So this is basically the Poisson bracket of this with the base is QP. So delta F is the change in the value of the function under the infinitesimal canonical transformation is given by the Poisson bracket of the function with the generator of that infinitesimal canonical transformation with this infinitesimal change in the value. Okay, so this is one important conclusion. And then if you put this, if you put my G as H here, so if I put my G as H here, then that is going to be or this function, not this G. So let us try to see what we have is like, so this is what we have is the change in the function of this F. This F is under infinitesimal canonical transformation goes to some QP to Q, and then this is the change in this value of this function is given by the Poisson bracket of that function with the generator of that infinitesimal canonical transformation. So this in this interpretation, the generator G produces basically the infinitesimal motion in phase space, and that could be the translation or as well as the rotation. Okay, so this we are going to see in a moment that how the G, when the G is going to give the translation, so what is going to be the generator of this infinitesimal canonical transformation, and if this G is representing the rotation, then what physical quantity is going to be the generator of the infinitesimal canonical transformation. And for now I have some remark here is that for F is equal to G, if I put F equal to H here, the Hamiltonian of the system, if my system is function is a Hamiltonian, then this change in the Hamiltonian is the Poisson bracket of Hamiltonian with the generator of the infinitesimal canonical transformation. And if G is a constant of motion, we know that if we take the Poisson bracket of something with the Hamiltonian of the system, and if that is going to be 0, then that particular function is going to be the constant of or integral of motion. So if this is going to be 0, if this is going to be 0, then G is that means T is going to be the constant of motion. So which implies that this delta H is going to be 0. So thus the infinitesimal canonical transformation generated by a constant of motion. So this is the generator of infinitesimal canonical transformation. So if this infinitesimal canonical transformation, the generator of that in particular infinitesimal canonical transformation is a constant of motion, and that leaves the Hamiltonian of the system unchanged. Okay, that is delta H is going to be 0. So if the transformation is going to be a quantity that is going to be the constant of motion, then that infinitesimal transformation is not changing the Hamiltonian of the system, that is not changing the equation of motion of the system. So this is important, because using this concept gives me the connection between the symmetry properties of the system and the conserved quantity. Because if that G is going to be the physical parameter or physical function which is a constant of motion, then that is generator of the infinitesimal canonical transformation, then that is not going to change the Hamiltonian of the system. And then when this is the situation, then you are going to have some conserved quantity, like we have in case of Lagrangian and Hamiltonian. We have seen that the linear momenta and the angular momenta, like the space homogeneity of a space and isotropy of a space. They both have given us that conservation of the linear momenta and the conservation of the angular momenta. So now we will going to see that what physical quantity is going to G, the generator of the infinitesimal canonical transformation, that if this is constant of motion, then this is going to unchange or leave the Hamiltonian unchanged, basically. Okay, so I'll end this lecture at this point, and in the next lecture we will discuss about this point. Okay, so thank you again, and let's hope we meet soon. Thank you.